Inviting me here. Thanks also to the Newton Institute for hosting us. I'll talk about singular Brascamp Lieb integrals. This is a bit maybe an extreme point of the subjects in this conference. There are implicitly a lot of half functions in this talk, and there are also a lot of singular value decompositions in this talk, and then there's a big question about a multi-scale analysis of these singular value decompositions. And I think there are very deep connections to a number of things we have heard here. I've actually thought this for a while. Unfortunately, the slides may not do this very explicitly, so I just wanted to say this at the beginning. Singular Brascamp Lieb integrals, in the words of Andreas, I may not have called always like this. It's always a social phenomenon how you call things. So let me tell you what a singular Brascamp Lieb integral is. Let's first talk about Brascamp Lieb per se. A Brascamp Lieb is a multilinear form on Schwartz functions. Now, if you think there's something called the Schwartz kernel theorem, that whenever you have a multilinear form on n Schwartz functions, then you can always take the tensor product of these Schwartz functions and pair them with some distribution. And that is the general multilinear form. And a Brascamp Lieb form is when this distribution here, which lives in this tensor space, when this distribution is simply integration over a hyperplane, all right, or a subspace more generally. So here we have an affine subspace. So delta is a Dirac delta function. Pi is a surjective linear map. So this delta basically integrates where pi is zero, the zero set of the pi. So this is a linear map. So the zero set of this linear map is a subspace, and we translate the subspace by a z, so it's an affine subspace. So this is the tensor product of Schwartz functions integrated against a affine subspace. And that's what's called a Brascamp Lieb form. We can change the variables, just shift the whole space and put the z inside here. So then you have these translated functions here, and sometimes, for example, we'll care about LP bounds on these forms. You don't really care about the translate of the function. So maybe this. So what I try to say is there's not a big difference whether you look at linear subspaces or affine linear subspaces. So if you replace the functions, you're back to this. Another observation is if this Zj, if this vector of Zj is actually inside this subspace, then you can move from here up here back. This Dirac delta is the same as this, provided Z is in the kernel of pi. And then you observe that your whole form actually has a symmetry under simultaneous translations of the functions f. All the three are equal, all right? And the value of your form applied to these n Schwartz functions is invariant if you translate all the Schwartz functions in such a way that this vector Cj is in the kernel of that space. So you just translate this in the space. Now you can take the Fourier transform of the previous integral. So if you have a distribution, it's integration over a subspace, a linear subspace, then the Fourier transform is the integration of the orthogonal complement of the subspace. So that's what's written here. If pi is an orthogonal projection, then 1 minus pi is the projection onto the orthogonal space, and here you're integrating the Fourier transforms of the Schwartz functions on the orthogonal complement. So therefore, on the Fourier transform side, this form is, again, a Brascamp Lieb form. In fact, it has a whole lot more symmetries now. Now you can translate the Fourier transforms in the subspace on this orthogonal complement of the subspace, and these are also symmetries of the form. In fact, the totality of all the symmetries completely determines the form. So given any form that has exactly those translation symmetries and those what's called modulation symmetries, so translating the Fourier transform is a modulation of the function itself. If you have a form with all these translation modulation symmetries up to a scalar multiple, it has to be exactly this. So these are highly symmetric. The Brascamp Lieb forms are highly symmetric objects. is often written, so I've written these integrals with a delta function here, which is an implicit way of writing the integral. You can also try to make it explicit. There's a subspace over which you integrate. You could try to parameterize the subspace with some coordinates. So some Rn is mapped into the big space, and the image is the space. And then if you write, you call x the element in Rm, you get an integral over Rm, and you get some linear maps inside the arguments, all right, which are just the components, ij. Well, here, maybe this is not quite accurate. I should be this map, and ij should be the j's component of this map. Now, we'll have to take the Fourier transform. Maybe today we won't be so explicit, but here's a Fourier transform calculation. So there's a little remark, if pi is not an orthogonal projection, you actually have trouble writing down something explicit here. You have to write down, you have to do a Gram-Schmidt and write down a lot of determinants. But passing from this to the Fourier transform is rather easy. So here you just apply the Fourier inversion formula. Every f is written by the Fourier inversion formula. You get these additional integrals. And then you do a Fubini, and you end up with the form, with the Fourier transform side in this delta form. Okay, a little calculation, maybe not so important today. So now, what's a Brascamp Lieb inequality? This is when we try to estimate such a Brascamp Lieb form by the product of LP norms of f. Only now it is that we split the symmetry between the functions and the Fourier transforms. All right. So the LP norm of f, of course, is different from the LP norm of f prime. The ij's need to be surjective, or else you're mapping on the set of measure 0, and it cannot be seen on the right-hand side. So now a remarkable thing is that you could ask under which assumptions on the p's and on this big subspace, which is encoded by these maps ij, do you have such an a priori inequality. And it's quite remarkable that you have an if and only if characterization named after Bennett, Carvey, Christ, et al. Or it's a condition on the dimension of certain spaces. So here you integrate over Rm, and you look at every subspace of Rm, and then you look at the images of this subspace under these maps ij, and then you look at all the, and then you need this inequality on the dimensions. And if V equal Rm, you actually ask for equality. Now the proof of this is very simple. The proof of necessity is very simple. So what you do is you've got this big subspace in this n-dimensional subspace, and what you do is you look at a big disk inside the subspace, and then you look at the one neighborhood of this disk in the big space, so you get a big slab. And for this slab, you can essentially calculate both sides explicitly, and then you let the radius of the disk tend to infinity, and then you of course need the behavior and the radius to be favorable for having such an inequality. This is giving this inequality. Now if the subspace V is equal Rm, you don't have to take this one neighborhood, because you already have an open disk, and you also have an argument as you shrink the disk to 0, and that's why you need equality. So this is a proof of necessity. The proof of sufficiency is a whole lot more complicated, and I won't go into this right now. So here's this inequality one more time. Like to make a few simple observations from this inequality, which you could also do directly from the Brascamp Lieb inequality. So first of all, just noting that these dimensions are at most as large as this dimension, you end up with this inequality. So that's an inequality independent of the projections that needs to hold just on the Pj. Now, if equality holds here, this is when the 1 over pj's are as small as possible, so in a way the pj's themselves are as large as possible. So if you try to go to large pj's, in average you get an equality here. If that if you have equality here, then you need equality in all these dimensions. So essentially the ij's need to be all injective, all right, because you're not allowed to lose any dimension relative to that. So if all the ij's are surjective, then of course the ij's are surjective, have to be surjective on all of Rm. They're also injective on all subspaces of Rm. So there's actually only one condition left. Only the condition for V equal Rm needs to be checked if you have equality. So that's one extreme case. The other extreme, what if you try to make the Pj as low as you can? Well, you will try to push them down and you reach 1 at some point, and you cannot go below 1. The simple argument, if 1, let's see, is it written here? Well, you would take V be the kernel of one of ij's, and then this shrinks by the dimension of the range. This also shrinks by the dimension of the range, and this cannot be larger than 1, or else you destroy that inequality. So these are two extreme cases. One equality here, the pj's are as large as it can. Pj going down to 1 is as small as. If one of the pj's is equal 1, then something particular happens. This is an endpoint of this range, and you expect maybe some surprises. And yes, L1 is nothing but the convex combination of all the Dirac deltas at all the points. So if you want to prove an L1 inequality, it's enough to plug in Dirac deltas, which we do here. We plug in a translated Dirac delta at place x1. You'll notice these are two Dirac deltas. You can tensor them into a big Dirac delta. Or in other words, this delta just says that x1 has to be equal to z1, so you plug x1 equal to z1, and then you're left with a Brascamp Lieb integral of lower complexity. So this endpoint, if the p's become 1, you're sitting at the endpoint, you can reduce the inequality to lower complexity. First, the integral to lower complexity, and then maybe the Brascamp Lieb inequality also. Now we come to singular Brascamp Lieb. So I view a Dirac delta, so I'm still sitting at this endpoint where one of the p's is 1, and I know I can plug in Dirac delta, and I just want to view a Dirac delta as a special case of a singular integral. All right, what's a singular integral kernel? That's, if you wish, well, that's a distribution or a function outside the origin, and it's got to have some dilation symmetries. All right. In particular, say on the Fourier transform, it's all right. So one example. Let me just write down the Hilbert kernel. All right. The Hilbert kernel in one dimension, 1 over t. That's a singular integral. Its Fourier transform is signum of tau with maybe an I pi. All right. So these are homogeneous functions. They have a dilation symmetry, homogeneous of certain degrees. The Fourier transform is always homogeneous of degree 0. How do you get a homogeneous function of degree 0? You take your favorite Schwartz functions and you average over all dilations. This is what's happening here. All right, and then the Fourier transform. On the spatial side, you've got the power lambda k, because you are not homogeneous of degree 0, but homogeneous of a certain degree, depending on the dimension in which you are a singular integral. And then this function is not going to be a locally integrable function, as we know from this example. So then typically, when you want this to be a distribution, you have to define a principal value sense. So here, the important thing is that you take this limit n goes to infinity only after integrating this integral, and then you have this is a principal value distribution. All right, so again, we think of singular kernels maybe most easily as certain functions on the Fourier transform side. The k hat is a smooth function outside the origin, homogeneous of degree 0. That's how we like to think of it. And obviously, the Fourier transform of the Dirac delta is a constant 1, which is homogeneous of degree 0 and smooth outside the origin. So the Dirac delta is 1. All right, and now we would like to plug in those singular kernels into the Brascamp Lieb. So the Brascamp Lieb takes this form. So the first h functions are actually Schwartz functions, and the last n minus h functions are actually singular integral kernels. All right, so this is what's a singular Brascamp Lieb. So singular kernels have a dilation symmetry. I mean, you could be more general, singular kernels without them, but for today, we just consider the homogeneous situation. So there's a dilation symmetry, but they don't have a translation or modulation. If you translate, except for the delta, which has a modulation symmetry, but these have neither translation nor modulation symmetry. The point 0 is special both on space and frequency. So you're destroying some of the translation and modulation symmetries of the form. This is no longer. But the original form had very many translation and modulation symmetries, and some of them may be such that they leave the k alone and only translate or modulate the f's. And this will be remaining translation and modulation symmetries of this form as a form in these functions f. Singular Brascamp Lieb inequality now asks the question, can you prove LP bounds in these functions when you have a number of single kernels? All right, one kernel would be the one parameter case, several kernels would be the multi-parameter case. So now, the reason why BCCT, Bennett Carberry Crystal, was so remarkable is that in this situation, you are very far from having a sufficient and necessary condition. And it's not just this. People have done, so the name Brascamp Lieb has been fashionable in some circles, and people are doing all kinds of, they're doing oscillatory Brascamp Lieb, nonlinear Brascamp Lieb, all kinds of variants of this Brascamp Lieb, and it's only in the classical BCCT where you have this if and only if. In all other settings, it's a complete huge zoo of things that could go on, and you are basically still at the level of case-by-case study. You start with low-dimensional, low-complexity cases and study them one by one. So there's no such thing as a general condition. In particular, here in this, so this one is just wide open in general. So there is some. So we want the singular Brascamp Lieb to hold regardless of what the singular kernel is, maybe with a certain normalization of the kernel to get the constant right. So in particular, Dirac delta is a singular kernel. So let's plug in Dirac delta for each of the singular kernels and see what we get. So we plug in this product of deltas, which is a tensor delta. This needs to be, a delta function always needs the linear map inside to be surjective, so we need this map to be surjective, or else the whole thing doesn't make sense and we can trivialize. So we assume this map is surjective, and then we can choose variables on the range, so we just call this th plus 1 and so on, tn, and we can use these numbers, these coordinates, as variables of our integration space in particular. So then integral looks like this, or it looks like before, except now I have no longer maps ij here, I just have tj, because the ij, I can just use the range of the ij to parameterize. So I got the t's, and I got the y's, and together they span this rf. So we've got a small a simplification, a normalization that we don't need to look at general maps over here, just because of this observation up here that this needs to be subjective. So there's no good, necessary, and sufficient condition. So let's look at some necessary conditions. And well, again, if we plug in Dirac deltas for the singular kernels, and we just end up with a Brascamp Lieb of lower complexity, and of course this better be bounded. So this gives you a condition like BCCT, where W is the kernel of these ij's. This is basically well, this is a space of y's. Okay, we have y's and t's, so W is a space of y's, and inside the space of y's, you need this Brascamp Lieb condition. That's a necessary. Now, from the singular integral theory, we know it's very important that this 1 over t has a sign change. So there's cancellation. The whole thing works. I mean, the bounds for the Hilbert transform is one example for singular Brascamp Lieb, and we know it's very important that there's a sign change. So it is under certain, if you do very general singular Brascamp Lieb, it's possible that you can plug in the kernel and the function and choose a function so that the whole integrand becomes positive. All right, and that's obviously not allowed, because then you can very quickly, then you don't see the cancellation anymore, and you get the absolute value, and it cannot be bounded. So a necessary condition is that the spaces need to be such that you can never completely kill the cancellation of the singular kernel, and here is, without details, one condition like that, and if one of the PJs is infinity, there's an even more refined condition. This is not a complete set of conditions. The philosophy is that you're not allowed to change to kill the cancellation. Now assume we have two singular kernels, so this is n minus 1 and n. Then there's also a case where one kernel destroys the cancellation of the other kernel. This is also a source of necessary conditions. So what we want to do is we want to plug in such functions, just a bump function with a certain quadratic modulation, all right? And if we choose the quadratic forms suitably, they just become in the sum over all j, that we just become this very simple quadratic form. Obviously, if you have enough functions and enough variables, you can always choose the q's so that this happens. And then just zooming, I mean, this is a huge integral, just zooming into the integral in Tn minus 1, you're seeing something like this. So you have, these are the kernels, the Schwartz functions that generate the singular kernels after dilation, and you're looking at such an integral, and you realize this phase is taking the Fourier transform of one of these functions, and then you get the Fourier transform of one of these kernels times the other Schwartz function. Now it's very important that the Schwartz functions have mean 0, so they must have cancellation, but if you're unlucky, there's two of them, and if they play together, one could destroy the cancellation of the other. If that happens, you also cannot have singular Brascamp Lieb bounds. All right, so there's this general phenomenon. You're not allowed to kill this, and this is the only source, the only good source of counterexamples why something as some singular Brascamp Lieb cannot hold. So now let's go to sufficient conditions, and again, they're far from the necessary conditions, and I'd like to put down some pictures here. So let's first look at the case where the p's are very small. So there's two extreme cases. There's small p's and then there's large p's, all right? So small means you're near 1. So suppose all the pj's are near 1, all the pj's are between 1 and 2, then you can just write this whole thing in the Fourier transform side, all right? We have seen this integral before. And then the k hats are just L infinity functions. They're just bounded functions. So you can just apply the standard Brascamp Lieb with L infinity in these, all right? And then you get something like this, assuming you have a BCCT condition on this setup here. And then you just apply the Hausdorff-Young inequality using that Pj is less than 2. You have a Hausdorff-Young inequality. And then for all the way from here to here, you have a singular Brascamp Lieb inequality. Right, this may be not a very interesting argument, but it is an argument. It works. It requires small p, and then it works under certain well-understood assumptions of geometry here. So this is all I will say about this extreme case, and then all the literature is actually about this other extreme. Very little. So there's a vicinity of this case described here, and that's understood. And then nothing has been done all the way down to the other extreme. So let's look at, and this is the large P means sum 1 over Pj equal 1. All right. So this is called the Hölder scaling. That's the one that has been studied extensively. Let's, for simplicity, look at only one singular kernel from now on. There's a lot of work on more than one kernel as well, but it's not for today. So, in this Hölder scaling, we said the whole BCCT condition, which of course is still a necessary condition if you plug in the singular kernel to be the Dirac delta, It just says that each ij restricted to W needs to be injective. All right? In fact, it also needs to be surjective by what we said before, adapted to the situation, unless Pj is infinity. Let's ignore it. Let's just assume the ij's are injective and surjective, so they are bijective. So all of them are bijective, so all of them are regular maps. In particular, the dimensions of the fj have to be all the same, because these maps are all surjective and they're all bijections from the parameter space. All right, and also, so recall we had written the singular Brascamp Lieb in this form where there was no I here and there was this I here, and the I now written in terms of matrix, a matrix acting on Y, a matrix acting on T. Now what is said here can be interpreted saying the AJs have to be all regular, they're all square matrices. But we can change, if we change variables here, or we rather rotate the F a little bit, which doesn't matter on the right hand side, we can assume all the AJs are equal to the identity matrix. So we get rid of further parameters like this. Right, so this is the general singular Brascamp Lieb in this situation. So now there is, so we are down here. Let's bifurcate this case a little further. Large P. So if you have a singular kernel in one dimension, all right, some 1 over t here, what you can do is you can rotate it in higher dimension and thereby generate, by superposition, a singular kernel in higher dimension. It's called the method of rotations. Now, if you can prove a bound on the more singular low-dimensional case by the method of rotation, you get bounds for the higher dimensional case. So therefore, as a rule of thumb, the estimates get easier when the dimension of the kernel gets larger. So if they're more, the dimension of this space here is larger, makes the whole thing easier. So let's look at the extreme. All right, so here is large, how's it called, large Kn, and make here small Kn. All right, so that's down here. We are in the Hölder scaling, but now we distinguish whether the space Kn, which is the space of the argument of the singular kernel, is large or small. So how large can this get? Well, if you put too many variables over here, you can't put them all over here anymore, so there will be some dummy variables here which do not appear here. All right, there's a certain fixed dimension here of Y. The matrix has a fixed size, so it's just so much you can do until you are no longer injective, right? So then you have something in the kernel. So if you've got some variables here that don't appear here, you can just integrate them out. If you integrate a singular kernel over a subspace, you get a singular kernel from the complementary subspace. So therefore, there's just an upper bound of what you can do here, and let's assume it's this one. Let's assume we are in this upper bound. Well, then each of these components appear exactly in one of the functions. Now you can do a rotation of this kernel in each component separately to get rid of the b's, because the b's now have to be regular because we are in this extremal dimension case. So you get rid of all the parameters. So this is the general singular Brascamp Lieb given our dimensional conditions. And it turns out this is actually classical. This should be the easiest case, and it's a classical so-called Koifman-Meyer theory. This encodes what's called paraproducts. So this is the whole paraproduct theory. You get a lot of LP bounds in the Banach range, P strictly between 1 and infinity. Now, this form, remember we are talking about translation and modulation symmetries of this. Now we have made the dimension of the kernel very big, so there's very few symmetries left that don't touch this kernel. In particular, if you look at this carefully, there are no modulation symmetries left on this form. Right? And there are no modulation symmetries in the classical theory. So if you wish, this is understood, this case is completely understood. Now let's go to the other extreme. What's the other extreme? let's make kn as small as possible, and obviously, well, kn equals 0 would mean you are a classical Brascamp Lieb, so that's not interesting, but kn equal 1 would be the minimal dimension of the kernel. Now, you still can vary the dimension of the functions. The functions have dimension k1, and if you wish, for fixed n, this gets more impressive if the dimension of the f is large, all right? So making the kernel small is relative to the dimension of the function, so you try to make the function dimension k1 as large as you can. Again, there's an upper bound. If you make it yet larger, then you get some dummy variables over here that don't see the kernel you could reduce. So this is the extremal case here at the very other end. It still comes with a parameter n, which is the number of functions, essentially. So then it turns out, well, the bj's, if t is one-dimensional, the bj's are vectors, and these vectors try to span as large a space as they can, so assume the vectors are all linearly independent. This corresponds to this case down here. If they're all linearly independent, again, you can change the basis here of this y space and just get rid of all the parameters. And then here's a special choice. It's written slightly differently from here, but this is sort of up to change of variable the same as this. So I'm giving you particular projections. You have n-1 variables, and the j's projection kills the i's variable. All right, it's just reducing from n-1 to n-2 dimensions, and you've got one of these projections for every entry here. So those are the projections you put in here. The kernel needs to be one-dimensional. Just write 1 over the sum of the xi, and so that is sort of, again, without parameters. So it's a unique guy that's sitting here at this most difficult slot. And let's see what's known about it. Well, the case n equals 3 because maybe, I don't know whether that's confusing, there's 2 functions and 1 kernel, that's why n equals 3, all right? So let's do this for n equals 3. We've got 2 functions, 2 variables, and it looks like this. Each function gets all except 1 variable. You see here, this is just the classical Hilbert transform, written maybe in a little funny way, and of course it's classically. There's lots of LP bounds known, in particular this bound is known, all right? So that's. Now the case n equals 4 looks like this. You've got 3 functions, and each of them gets all except 1 variable. All right, so I'm putting this in a cyclic fashion here, and then that's the curve. Now you have Hölder scaling. You would assume any kind of Hölder bounds like this. 3, 3, 3 should be the simplest one, because if you have any bound by symmetry, you have the symmetric bounds. You interpolate to get the midpoint, and that's this one. All right, that should be it. But it's not known. So in fact, no. For this object, no LP bounds are known. I consider this, well, if you wish, everything I've said so far, the purpose was to highlight that this is the main open problem in the area. Of course, you have these guys then for larger n as well. Now this one, I think this one seems to be maybe in reach. The other ones I will only call when once I have seen this one. So I've spent some time working on this. We have some partial progress. So we've got this bound. If one of the 3 functions has a very particular form, it's this elementary tensor and skew variables. All right, and it's a little bit of a lie, because we really only have this in the so-called Walsh model that Andreas mentioned. So also, I can write down a H function model of this. This is where the H functions come in. Also, what's playing a role, you read these functions in the proof of this. What you do is you read these functions as, if you have a function, you can read it as the integral kernel of an operator. So you can define an operator like this, integral f of x, y, phi of y, dy. And then in the proof, you're led to making a singular value decomposition of these operators at all scales. You cut this function to a square, and then you make this, write down this operator and do a singular value decomposition of that. And the reason we can treat such things, if you ignore the F2 for the time being, if the kernel is of this form, then this essentially means that the operator is a convolution kernel. its singular values decomposition is basically the Fourier expansion of the operator, and we are doing Fourier analysis, and that's how we know how to deal with that in this particular situation. In the general situation, we have general singular functions, and we have to do a multi-scale analysis of this, and we don't know how to do this, except in very particular situations. Not just this, there's a few more. Another partial progress is, well, if you can't prove this, let's do the following. Let's truncate the kernel so that it's zero outside this region. All right. Now it's actually an L1 function with L1 norm log R, and you can apply the classical Brascamp Lieb. All right. If this is an L1, you have the classical Brascamp Lieb, and you get this bound with log R in here. And now you could say, well, we really like to get log R to the 0th power, but log R to the half power is halfway to that from the trivial log R. All right, so you can make a race how good a power you can put here, and we can put half power. So there is, I like to skip a few because I'm running. Well, actually. So this was talking about this case. Now how about the intermediate cases? Well, I should be saying, so in the two extreme cases, we could get rid of all the parameters bj, all right? We've got these parameters bj. Now in the intermediate cases, the bj's do matter. You cannot just get rid of them. They can be in generic position or not in generic position. So if they're in generic position, there are some positive results, and this is maybe what's subsumed under the notion time frequency analysis. So there's a lot of the so-called bilinear Hilbert transform is one of those. I kind of want to be quick on this. So this slide says that we can go halfway. There's some interesting additive combinatorics coming into play. This is time frequency analysis, the classical Carlson technique, outer measure approach, etc. I'm not going to go into that. So this is a small dimensional case. This is sort of the smallest case sitting down here, which looks at what the B's are. This is the smallest case, which is neither of the two boundary cases here. It's called the bilinear Hilbert transform. The B's are just numbers. And basically, the generic positions, they're all different. In the degenerate position, two of them could be equal, in which case you identify the pointwise product. So you see how things bifurcate. There's a bunch of results. If you go a little higher, same three functions, but now x and t are two-dimensional, so B is a 2x2 matrix. Again, the B's could be a generic situation, or they could have coincidences such as common eigenvalues. So the problem here is if you have common eigenvalues, or rather you can normalize one matrix is 0, one is the identity matrix, and the third one is in Jordan canonical form. Now the third one could either avoid the eigenvalue 0, 1, or it could have the eigenvalue 0, 1. It could have both eigenvalues 0 and 1. That's a phenomenon that doesn't appear in one dimension. So there is identified 9 different cases of this. So now we are sitting, if you wish, we are sitting somewhere near here, the next smallest case. So what I wanted to talk about, or I have maybe a few more minutes, what I like to talk about is this case when one eigenvalue is 0 and one is 1. It looks like a very degenerate situation. It's not the generic situation up here. It's degenerate. There are all these degenerate situations sitting like a sort of algebraic variety inside this set, and there's a whole different story, of course, from the generic case. So there's this particular case which is completely generic, and there is a theorem about this case, and the theorem is in higher dimensions. So let me just write down, let's see, they ought to be. So I'm trying to give you a singular Brascamp Lieb form like this. There's functions, there's kernels. I'm trying to describe what all this is. So the projections all go down from 2m, R2m to Rm. And how do they do it? Well, we take R2m and we split it as two sets of m variables each. All right, and then the projections choose for each of the indices 1 to m, either the guy from here or the guy from here. All right, so this is what Pj does. J is a map from 1m to 0, 1, and the projection picks correspondingly, and this should be an xm. This should be m down here. Sorry for that. All right. So there's 2 to the m such projections. They naturally can be considered sitting on a cube. So the set of these functions form a cube. Here I have drawn the cube in a small dimensional case. All right, and if you wish, at each corner of the cube sits such a projection, which chooses 0, 0, 0, 1, 1, 0, 1, 1, and so on. And it comes with a function, so each corner has a function. And then the variables, each function takes 2 variables, namely x1, 0, x2, 1. All right, so each function takes the variables that are in the adjacent edges. This is a way you can draw a big cube and this combinatorial data of these projections. Now there is a kernel K, and this pi is another general projection from 2m to m. And the question we posed ourselves was whether we can prove bound, whether we can understand for which projection is pi, given these fixed projections we can prove bound. So this corresponds to this one case I mentioned before. And here is the theorem. So indeed, if you do have these Brascamp Lieb bound for the symmetric point, all the p's are equal, and they have to be that. And you need the BCCD condition, which says nothing but all these. There's an injectivity condition, which means that these maps are all non-degenerate. So there is. Now let's see. Maybe I have a few more minutes to show you a movie. So the proof of this goes. Let's see. So let's talk about the case n equal 2. All right. So we got 4 functions. We are sitting in this, having this structure of functions and arguments. And let's see how this works. And first of all, let's pick, for the positive result, let's pick a particular projection, and let's pick this projection. All right, we need 4 variables, x1, x2, y1, y2. We need to project down to 2, so that's how we do it. And then this is how. So I've written the x0 and x1. I have written x and y now to say. And let's say we like to prove this to be bounded for all functions in L4. And let's normalize the L4 norm to be 1, so we need to bound this by a constant, assuming all the L4 norms are 1. And as a warm-up, our most favorite singular kernel is always the Dirac delta. So let's plug in K, the Dirac delta. What does it mean? That means that x1 should be equal x2, and y1 should be equal y2. So there's only a x and a y. The whole thing looks like this, and you recognize Hölder's inequality. All right, and since all the norms are normalized. So that is. So now I would like to do the next warm-up step. So the Fourier transform of the Dirac delta is the constant function in the plane, right? There's x and y. So I'd like to write the constant as a sum. This is a typical cone decomposition in little Paley theory. I'd like to write the constant function as a sum of 2 functions. One is essentially supported in this cone, and the other one is supported in the other cone. And I don't want them to be sharp cutoffs, I want them to be smooth functions, always a bit fuzzy. And the way I do it is as follows. So here's the Dirac delta that I would like to decompose into 2. I take bump functions. This is the heat kernel bump function. This is the derivative of the heat kernel. This has mean 0. This doesn't have mean 0. So I can write the Dirac delta as a limit of Gaussians that focus to the point. All right, so that's what's happening here. And I'd like to separate the x1, x2, so I'm doing this convolution of 2 Gaussians, which then is a Gaussian and x1 minus x2, and in the limit becomes this, all right? Now this is a limit as t goes to infinity. If t goes to 0, the whole thing goes to 0. So I can write by the fundamental theorem this limit as an integral of the derivative from 0 to infinity. Okay, so now and now the derivative by the Leibniz rule falls on one of the 4 functions. If it falls on one function, it's taking a t derivative of one function, which, because it's the heat kernel, is the same as a double x derivative in that function. A partial integration in p will put it over there. So punchline, instead of getting 4, these I only get 2, and each of them has 2 derivatives, 2 spatial derivatives, all right? So these are the 2, this this is breaking up the Dirac delta in two, and those are the two. And so the rest is more or less a movie. So now I'm writing, so this is one cone. I've written the kernel in this complicated integral form, and there's two red functions which have capricious mean zero cancellation for us, and they are sitting in these variables. All right, so that's why I'm putting them red. And the other cone looks like this. The other two are red. Okay. So one thing I can do if I stare at this, I can. So this red color is very precious. I can do a Fubini to bracket. So the red color here, this depends on x1. I Fubini all the functions with x1 inside here, and all the functions with x2 in here. So these red integrals are the ones remembering the cancellation, and everything black here is positive. I can do a Cauchy-Schwarz. I can read this as pairing two functions, and I do a Cauchy-Schwarz. Okay, I can do a Cauchy-Schwarz. Those are the same, and there's another term with the other one. Aha! I don't have terribly much more time. So let me. So this is what we try to bound, and we can do a Cauchy-Schwarz. What does a Cauchy-Schwarz do? A Cauchy-Schwarz, we will bracket say this and this separate, and then do Cauchy-Schwarz. So what's happening is this becomes equal to that. All right. So this is after Cauchy-Schwarz, enough to prove a bound on this. Now we know there's two cones, and the sum of both is a Dirac delta, which we know how to bound, so we can estimate the other cone instead. So we put red here. Now we can do the Cauchy-Schwarz the other way. So we double up, and now this corner gets copied over here. Now it's completely symmetric. All right. And now we can continue. We can again switch to the other cone. We can do more Cauchy-Schwarz, but you see the whole process stabilizes. So each of the cones is already its own Cauchy-Schwarz, which means each of the cones is per se already a positive quantity, because the right-hand side of Cauchy-Schwarz is always positive. So you add two cones, and both are two positive numbers, and you know the sum is bounded, therefore each individual is bounded. So the whole purpose of the symmetrization was to make sure that the cone decomposition is into two positive terms. So that is essentially the proof that there's pictures in higher dimensions. Let me just show you the movie, all right? So you can also do this with simplices, which is then giving you this log improvement of the simplex Hilbert transform F. All right, I think I've just made it.
Thanks, Christoph, for this nice presentation. Are there any questions or comments? Or one or two before the coffee break?
Maybe I'm wrong, but I had ideas that initially Brascamp Lieb inequality was related with log concave function and measures.
Yeah.
Do you have some connection, because I didn't understand?
Yeah, no. No, I mean Brascamp Lieb. There was a paper by Brascamp Lieb essentially proving bounds on these operators, doing, among other things, as you said, log concave. Then come 30 years later, and then there's this Bennett, Chris, Carberry-Tao, and they have a paper, and they say on the Brascamp Lieb inequality, and then they prove their by now famous condition. Then there has evolved a whole community of people who call these things Brascamp Lieb. I'm with you that there's a bit of a detachment from the original purpose of Brascamp Lieb did to what we are doing here. So that's correct. And in a way, I feel a little bad. I'm branding. So these multilinear operators, I've done them all my life. I've done them 20, 30 years. I've never called them Brascamp Lieb. I've just started calling them Brascamp Lieb because right now there's a huge fashion of doing Brascamp Lieb, nonlinear Brascamp Lieb, oscillatory Brascamp Lieb, etc. So it is. So I have the story. I think I gave you the reasoning why I call it like this. I'm with you. It's a bit of an arbitrary naming here, but that's how history works. Our naming is always a little bit. Andreas was saying something like this about the half functions. Okay.
Further questions? So then that's not the case. Let's thank Christoph again.